So last week we were discussing, of course, the first order factors or first order zeros and poles, and based on that we learned how to do the Bode plots. We're going to look at the phase Bode plots now. Magnitude Bode plot we discussed last week. Phase Bode plot of first order factors. And after this, we're going to do the second order, which is complex conjugate roots. Phase Bode plot, again, approximation we are using, not the exact one. Of course, exact are always can be drawn using the computer. But the whole idea of Bode plot is that you can draw an approximate curve without even going towards the computer. So you can have an idea as how the frequency response is going to look like in the decibel scale. Phase Bode plot, what approximation we are using? Let's look at that. So again, you have a single order pole. Either you're going to have 1 over 1 plus j omega over omega naught type of factor, or 1 over 1 plus s over omega naught, or you will have, of course, a 0, 1 plus s over omega naught. S is equal to j omega. So you're going to have either a pole or a 0. If you have a 0, that is, your transfer function is of type of 1 plus j omega over omega naught. The phase response of this, as we know, is arctan of imaginary over real. So arctan of omega over omega naught. The approximation that we are using is if omega is less than 1/10 of omega naught. Let's draw it here. So let's say this is 1/10 of omega naught. This is omega naught, and this is 10 times omega naught. So if your frequency is 1/10 of omega naught or less than 0.1 omega naught, we assume that omega over omega naught is 0. That is, omega is much smaller than omega naught. And of course, arctan of 0 is 0. So we assume until it hit 1/10 of omega naught, we assume that the phase is 0. And if the frequency is more than 10 times omega naught, we assume that that number is very large, omega over omega naught. And arctan of a very large number, of course, is 90 degrees. So any frequency more than 10 omega naught, we assume that the angle phase is going to be 90 degrees. Eventually, it's going to hit there. But again, for approximation, this is what we are approximating. And at omega is equal to omega naught, arctan of 1 is 45 degrees. So at omega naught, it's going to be 45 degrees. So you're going to have a slope, and the slope you're going to have a line, and the slope of this line is going to be 45 degrees per decade of the frequency. So again, that's an approximation of the phase Bode plot using of the phase plot using the Bode plot concept. And as you saw, the Bode function in MATLAB, it does not do this. It calculates each value based on the frequency and draw the exact phase Bode plot. But again, the whole idea of Bode plot is to, as I said, is to have the approximation, so you can easily draw it or easily have the idea as how the phase as well as magnitude Bode plot is changing. Just by looking at the equation, you can have an idea how it is changing instead of going and plotting it, plotting the exact values. The same thing is going to be applied for your 0. So this is for the 0. So this is for angle of h of j omega is equal to tangent inverse of omega over omega naught. That's the Bode plot for this function, and the Bode plot for if you have a pole, it's going to be exactly the same, except it's going to go down. With the slope of negative 45 degrees per decade. So this is for the pole. All right, what will be the phase angle for the pole for if you have this? If your h of j omega is 1 over 1 plus j omega over omega naught, what will be the phase angle for this? Expression for the phase angle. Negative 90. Say it again. Negative arctan of omega over omega naught, yes. Phase of the numerator is 0, and phase of the denominator is tangent inverse of omega over omega naught. So phase of the function is going to be numerator phase minus denominator phase. Negative arctan of omega over omega. And that's why you see over here that it is going down with the slope of negative 45 degrees per decade, and it's going to go until negative 90 degrees. So this is for this. So that's the first order pole and first order zero. That's how you're going to do the phase Bode plot for that. If your factors have multiplicity, square power or cube power, the slope is going to increase. Instead of negative 45 decibel, let's see what do we have here. Okay, so it has a square function. Let's do this and then we'll discuss it. So draw the phase Bode plot of this function. Gj omega is equal to 200, and then I'm going to take this out times 1000, 1 plus j omega over 1000 over s plus 10 is square, so I'm going to take 10 and 10 out. That's going to become 100. 1 plus j omega over 10 is square, and then I'm going to take 100 out from here. 1 plus j omega over 100. Let's do both. Let's do the Bode plot, the magnitude first, and then we'll do the phase for this so that we can get a little more practice. And I'm going to jump right into drawing the Bode plot. So first do the magnitude. Let me do it here. All right, so magnitude Bode plot. It's going to be 20 log 10 of the magnitude of this thing. So let's write, I'm not going to write down the whole magnitude, but Let's see. So this 100 is gonna be 10. There's 10 is 10, and 200 over 10 is 20. So that's gonna be 20. 1 plus j omega over 1000, magnitude of this factor. All right, so what is the magnitude of 20 log 10 20? What is that value? Who's gonna tell me? How much? 26. Okay, so let's go and draw a line at 26. Let's do it with green color. Let's say 26 is somewhere here. So that's gonna be the constant 26 decibel, corresponding to 20 log 10 of 20. All right, you have only 1 0, and then you have 3 poles. That 1 0 that you have, how it's going to behave on the Bode plot? Who's going to tell me? 0 until what? 0 until what frequency? 1000. 0 until 1000, and it's going to increase by 20 decibel per decade. Okay. So 1000, and then at 10,000 it's going to be 20. Put a point over here just so that we can create this line. Okay. So 1 0, and that's the Bode plot of that 0. Now we have 3 poles. What will be how this factor is going to behave? 1 plus j omega over 10 squared. Hold on. Yes. Negative 40, exactly. At what frequency? 10. Okay. Until 10, it's 0, and then it's going to go down by negative 40 decibel per decade. So negative 40 decibel. Start at 10, and then so at 100, it's going to be negative 40 decibel. It's going to go and hard for me to draw here. Give me a second. Yes, go ahead. You can start at any frequency, does not matter. You can start at any frequency, you just have to show that it's a logarithmic scale. You can start at 0.1, you can start at whatever, just don't start at 0 because again, log of 0 does not exist. Go ahead. Or you can start, in this case, you can start at 0 as well, actually, because you don't have omega, j omega. I'm sorry? 100 omega, which one you have mentioned? This factor or this factor? This one? It's going to be negative 40 because it's dropping by negative 40 decibel per decade, right? So in 1 decade of frequency from 10 to 100, it's going to drop by negative 40 decibel. That's why I just put a point here. I mean, this is a point here. So I just approximately put a point here, which is a little lower than that, and just connect these 2 points and just extended it. Yeah. The whole, yeah, in 1 decade of frequency, it's going to drop by negative 40 decibel because it's a square power. So each one of them, if you do 1 plus j omega over 10 times 1 plus j omega over 10, each one of them is going to drop by negative 20 decibel per decade with the same frequency. So they will overlap. So when you add them together, the total drop is going to be negative 40 decibel per decade. And the third one, negative 20 at 100. So starting at 100, at 1000, it's going to drop by negative 20. And then it will extend. Okay, so these are our individual lines, and then let's go ahead and 26 decibel until 10. Between 10 and 100, it's going to drop by negative 40 decibels. So 26 minus 40 is negative 14, right? Negative 14. So at 100, it should go to negative 14. Let's say here. The slope of this line is negative 40 decibel per decade. All right, at 100, how it's going to drop? Now you have two poles starting at 100. Well, one pole is started, two poles started at 10, and one pole is starting at 100. So what will be the slope now? Negative 60, yeah, it's going to drop with an additional 20, will make it negative 60. So between 100 and 1000, it's going to drop by negative 60 decibel. That means negative 14 minus negative 60 is negative 74. So let's say it's going to go down. Let's say this is negative 80. So 70 is the middle, and negative 74 is somewhere over here. Negative 74. So it's going to go down to approximately 1000. Again, I'm not drawing very, this doesn't look like it's dropping by negative 60. If I connect these 2 points, it will be sharper. So let me draw it like this, at least to show that it's different slope. And negative 60 decibel per decade, approximately, right, 1000. And at that 1000, your 0 is going to start, which will cancel one of the poles. So it's going to go back to negative 40 decibel per decade, the slope of this line. This is negative 40. Let me align it with that line. Negative 40 decibel. All right, let me do this real quick. All right, gain of the function is 200. 1000. 10, 10, and 100. 10, 10, and 100. So that's how it's going to look like. Negative 40 decibel line here, negative 20 decibel, and positive 20 decibel, and 26. 26. A cleaner plot to show negative. Negative 40 decibel per decade. Negative 60 decibel per decade. And then again, negative 40 decibel. All right, let's go to the phase Bode plot now. Right, our function again is this function right here. Now, phase Bode plot, of course, let me write this down again so we don't have to go back and forth. So you have point E 1 plus j omega over 1000, I guess, right? 1000, 10, and 100. 1000. So this is our gj omega. Phase Bode plot, angle of g of j omega. Of course, angle of constant is 0. So there's no angle. This real value is at 0 degrees. The phase of this will be arctan of omega over 1000. And then you have negative arctan of, I'm gonna write this twice first to let everyone understand it, and then we're gonna do the slope. We're gonna change the slope then. So this is omega over 10 minus arctan of omega over 10 minus arctan of omega over 100. Each factor, angle associated with each factor. Question about this equation, anyone? Looks good. So observe, when you have the square power, then you have 2 arctan, you're going to add them together, and you're going to get 2 times arctan of omega over 10. And now we're going to do the Bode plot, phase Bode plot for this. Let's go ahead and insert another slide. I'm sorry? 20, yeah, 20 is 0 phase, right? It lies on the real axis. Yes, it's 0 phase. So this is in degrees. And since we are dealing with 10 frequencies, so let's start at 1, 10, 100, 1000, 10,000. All right, let's look at the first one now. Arctan of omega over 1000. How it's going to behave on the Bode plot until omega is 1/10 of the cutoff frequency, which is going to be 100. It is going to be 0. 10 times the frequency, which is 10,000, it's going to be 90 degrees. And at 1000, it's going to be 45 degrees, right? That's what we discussed on this slide right here. So 1/10 of omega naught is 0. 10 times omega naught is 90 degrees. And at omega naught, it is 45 degrees when you do the approximation. So 1000 frequency is our omega naught for the 0. So until 100, 1/10 of 1000, it's 0. At 10,000 and more than 10,000, let's see here, it's 90 degrees. And at 1000, it is going to be 45 degrees. This slope is 45 degrees per decade. This is 90 degrees. That's for the 0. Now we have 3 poles. Make sense? Yeah. So for the phase Bode plot, the rule that we are using, the one we discussed, is until 1/10 of your frequency, we assume that omega over omega naught is very small. And we assume it to be approximately 0. So tangent inverse of 0 is 0. When you put the frequency 10 times the cutoff frequency, 10 omega naught here is 1000. So when you go to 10 omega naught, which is 10,000, we assume that the value is very large. And the large number, tangent inverse, correspond to 90 degrees of large number. So we put 90 degrees. And at omega is equal to omega naught, omega or omega naught will be equal. Tangent inverse of 1 is 45 degrees. So we put a 45 degrees at omega naught. Remember, this is again approximation. You do the exact plot. Exact plot is going to have some curve over here. It's not going to be straight line, but it's going to be curve. It's going to go to 90 degrees for sure, but it's going to have a little bit of curve before it goes to the 90 degrees. And the 90 degrees is not going to achieve at 10,000. It's going to be farther down the frequency. Eventually, it's going to hit 90 degrees. Second term, or you can do, yeah, let's do the second, or you can do this term first before we go to this. Arctan of omega over 100 and negative sign. So until omega is 1/10 of 100, which is 10, this is going to be 0. At omega is equal to 1000, it is going to be negative 90. And at 100, it's going to be negative 45. So 1/10 is going to be 0. At 100, it's going to be negative 45. And at 1000, it is going to be 90 degrees. Seems like my 90 here is different height than this. But anyways. This is negative 45 degrees per day. And this corresponds to the third factor, this factor, arctan of omega over 100. At omega is equal to 100 is 45 degrees, and at 1000 it is 90 degrees. Now the second factor, which has 2, so remember, arctan of omega over 10, how is going to behave? Without 2? Okay. So arc 10 omega over 10 until omega is equal to 1 radian per second, 1/10 of 10 is 0. At 10 is negative 45, and then at 100 and above 100, it's going to be negative 90 degrees. Now you're multiplying that by 2. That means all of those angles are multiplied by 2. So your slope increases, instead of negative 45 decibel per decade, it increases by negative 90 decibel per decade, and the final value is going to go to negative 180 degrees instead of negative 90 degrees. So we're going to go and until 1 is 10, right? Until 1 it is 0. So actually I should have started at 0.1. That's okay. Until 1 it is 0, right here. And at 10 it is 45 degrees. So let's go ahead and put a 45 degrees here. It's going to be 90 degrees, sorry, 90 degrees, because we're multiplying by 2, 90 degrees. And then 180 degrees at 100. So I'm going to drop it down. Should put a dotted line actually. Oh, it's hard for me to do that. That's negative 180 degrees. And the slope is negative 90 degrees per decibel per decade. So that's a square. If you have cube, of course, then every value is going to be multiplied by 3. So your slope is going to be, instead of negative 45, it's going to be negative 45 times 3 degrees per decade. Yes? Hmm? 90. So j omega 90 degrees. It's constant 90 at all frequencies. Right, exactly. Constant negative 90 degrees at all frequencies. Yeah. The same way as if you have a negative value, negative 2, that's 108, negative 2 is 180 degrees or negative 180 degrees, is the same thing. So whichever. Now we're going to add everything together according to our equation, this equation. Add and subtract these two, of course. In this case, add all of them. So we are starting at negative 90 decibel per decade until 10. And then we are going to start at, we're going to continue with negative 45 plus negative 90, negative 135 decibel per degrees per decade until 100. So it's going to be even steeper. So negative 135 and minus 90 is what? Negative 225, right? Negative 225. So it's going to go to negative 225. Actually, let me see. It's going to become a constant value as well. Negative 225. At 100. And then negative 45 and positive 45 slope will cancel each other, and you're going to have only this. So it's going to, oh no, that's going to be, oh, it's going up to here. So 1000. Okay. So this is start canceling each other. So up to this point, you're going to have negative 45. And then it's going to, let me see, it's going to 1000, right? Yeah, 1000. And then it is going to increase. You're going to have 90, negative 90, and negative 180. So 90 and negative 90 will cancel each other, and negative 180 will left. So it's going to go to, actually, let me see. May have to drop it earlier, because the final value is going to be negative 90. This 90 and this negative 90 will cancel each other. What is that? At 10,000, it's going to go back to that, right? Yeah, over here, 10,000. Yeah, that's true. So let's see at 10,000. That's negative 90 decibel. This is negative 135 degrees per decade. And then this is going to, so this one is going to increase by 45 decibel per decade, 45 degrees per decade. And finally, it's going to be negative. Let's just make sure this is going to negative 225. So you have negative 45 and negative 180. Yeah, it is going to negative 225. So that's going to be the phase Bode plot for this function. Yes. How did I get what? Negative 98. Where is negative 98? Oh, this negative 90 degrees. Yeah, sorry. Yeah, it looks 98, but it's negative 90 degrees. And this says 45 degrees, not 95 degrees. I can fix it quickly, so there's no confusion. Negative 90 degrees, and this is 45 degrees. Yeah. Okay, hold on. Let me, this is not negative 90. Let me move this up a little bit. Negative 90 is this line. So this is negative 90 degrees per decibel. Okay, and then this is negative 135 degrees per decade. Yes, so what was your question? Negative 225. Yeah, because observe here, you have negative 180 for this line, you have negative 45 for this line, and that is still 0. So negative 45 and minus 180 is going to be negative 225. Yeah, and it's going to go this negative 225 until this point right here, because at this point this negative 45 is going down and that positive 45 is going up. So these two will cancel each other, the green one and this one. So the only thing that will be left is going to be just this line, keep going at whatever was left, negative 225. And then finally it's going to go to negative 180. Okay, so that's the phase Bode plot, and that's the approximation for, again, first order roots. And now we're going to look at the second order system real quick. All right, second order systems. So second order system, we know that second order system equation can be written as s square plus 2 zeta omega n s plus omega n square. Zeta, of course, is the damping ratio, and omega n is the natural resonant frequency of the second order system. When you put S is equal to j omega, then j omega square plus 2 zeta omega and j omega and omega n square, you're going to get this. This is incorrect right here. I forgot to fix it. So this thing is, we are taking omega n square out from this equation, which will become j omega over omega n square plus j 2 zeta omega over omega n plus 1. So I don't know why did I put 1 over omega n over there. So omega n square is the common factor that we took out from there. The constant omega n square contributes towards the total gain of the system. So we don't really have to concentrate on that factor. We have to concentrate on the second order system, which is j omega over omega n square plus 2 j2 zeta omega n. So this thing, of course, j square is -1. So that's -1 omega over omega n square, this factor. So we can write this down as real part is 1 minus omega over omega n square. That's the real part. And then the imaginary part is j2 zeta omega over omega n. Omega over omega n is, we consider that to be a normalized frequency. And we just assume that a variable, assign it a variable u. This is the normalized frequency. Omega is, of course, changing. Omega n is constant. Omega over omega n we can consider as one variable. And we assign it as u. So we can write that equation down as 1 minus u square plus j2 zeta u, which is right over here. That's for the pole. Generally, of course, we're looking at the pole instead of 0. The second order equation is usually in the pole. So we are looking at poles right now instead of zeros. So 1 over 1 minus u square plus j2 zeta u. Now the approximation. Magnitude can be written as, of course, 20 log 10 of 1 over 1 minus u square j2 u, or 20 log 10 1 over 1 minus omega over omega n square plus j2 zeta omega over omega n. Magnitude of that, omega over omega n, of course, we are taking as u. So 1 minus u square plus j 2 zeta u, which we can write, of course, as 20 log of 1, which is 0, minus 20 log of the denominator. So negative 20 log of the magnitude of the denominator, which will be square root of the real part square plus the imaginary part square. Now the approximations for the Bode plot, and this is the approximation that you see, that we assume if omega is quite smaller than omega n, and generally quite smaller, we assume 1/10, as long as omega is 1/10 of omega n, so 0.1 times omega n, generally that is assumed. 1/10 of omega n, we can write it down. That's what it is usually assumed. 1/10 of omega n. Then we assume that omega over omega n is very small, it's approximately 0, and u will be approximately 0. So it's going to become 1 square plus 1 square basically. So it's going to be 0 until that point. So magnitude response is going to be 0 until that point for the second order system. So until 1/10 of the frequency, natural resonant frequency, your response is going to be 0 for the second order system for the pole. And we assume if omega is much larger than omega n square, again, generally 10 times omega n, that is usually assumed. If omega is approximately equal to 10 times omega n, that's considered to be much larger for the approximation, like we did for the phase Bode plot. Then we assume that omega over omega n is very large number. We drop that one, this one right here. We drop this one over here. And we assume that u square to the power square is the dominant factor. So we drop this one, and we also do not consider this because we assume that u square of a square is the dominant factor. And the gain will go down with the slope of negative 40, slope of 40 decibel per decade, or negative 40 log 10 of omega n omega. So basically what we assume here, if omega is greater than 10 times omega n, we assume that this factor becomes negative 20 log of the square root of omega over omega n square and the square of that. Square of that. Which means that square root and a square is cancelled out, and you're going to have negative 20 log of omega over omega n square, which will be negative 40 log of omega over omega. So it goes down by negative 40 decibel per decade after 10 omega n approximately. When omega is equal to omega n, u is going to become 1. So the first factor is going to become 0, 1 minus u square, and the second factor is going to be 2 zeta square root of that, which means 2 zeta, negative 20 log of 2 zeta. The difference between the actual magnitude curve and the asymptotic one, because we are doing the asymptotic one, which is the approximation, is a function of the damping ratio and must be accounted for when zeta is less than 0.7071. Now, without going into derivation, the resonant frequency at which the peak value of the curve is going to occur is given by omega n square root of 1 minus 2 zeta square. And that's why you see that zeta is less or equal to, is less than 0.7071. When 0.7071 is zeta, which is 1 over square root of 2, then omega r is going to become 0. If zeta is 0, then omega r and omega n becomes equal. So resonant frequency and natural resonant frequency becomes equal to each other. So this is what's going to happen at omega naught. This is u basically. U is equal to 1. And the peak value, as you can see, as the zeta becomes smaller and smaller, the peak is increasing. As we know, zeta value controls the peak value. As the damping ratio becomes smaller, your peak increases. As the damping ratio becomes larger, it starts going down towards your overdamped system. So the peak starts getting smaller and smaller. So for the approximation, what we are doing is we are going until 1/10 of omega n, and we are assuming it to be 0. And then we go 10 times omega n, we drop the curve, the plot by negative 40 decibel per decade. Between 1/10 and 10 omega n, we'll have to figure out what will be the peak value at omega r. And then we just put a point at the peak value and approximately just connect those points when you're drawing it by hand. Of course, if you're drawing it using a computer, it's going to give you the exact curve. So that's the easiest way to kind of look at the second order system. Go until 1/10 of omega n 0, after 10 times omega n, negative 40 decibel per decade, and between 1/10 and 10, find the omega r frequency, the resonant frequency, at which frequency the peak is going to happen. The peak can be calculated using this formula right here. Maximum value of the gain at omega r, 2 zeta square root of 1 minus zeta square inverse, which basically is 1 divided by 2 zeta square root of 1 minus zeta square. Zeta is less than 0.707. Because if zeta becomes greater than 0.707, you're going to have a square root becomes negative. So that's going to be the peak value at omega r. So you calculate what is omega r, calculate the peak value, put a point over there, and then just connect to that point. It's not difficult. You just need 3 points, 1 point at 0, which is 0.1 omega n, and then at 10 omega n, it's going to be negative 40 decibel, and then just find omega r and calculate the peak value, and then just approximately connect this. Again, it's going to be approximation. If you're drawing freehand, in between, of course, you don't know how it is increasing, what's the exact value, but just approximately, you can show the curve. Of course, computers are used for the exact curve. Did I start recording, by the way? I don't think I started recording. No, I did start recording. Yeah. Yes. To the next slide. Mm-hmm. 1 minus 2 zeta square. Why did you say that? That is correct. Oh, okay. I see what you're saying. Well, zeta has to be less than 0.7071 because of this, I think. Because omega, if it is greater, then here it's going to become negative frequency. So that's the value of zeta less than 0.707 is coming from here. Now, this is from the book. I'll have to go and check. For this one, yeah. If I take 0.5 square of that, 1 minus 0.5 square, you mean? So if it is greater than 0.707, so 0.707 is 1 over square root of 2. If you have 1 over square root of 2, so 1/2, that's going to be 0.5 at 0.707. If it becomes greater, this is still going to be positive. This is still going to be positive. But this value is coming from here, I'm assuming. Again, I just picked up these values from the book, from the textbook, without thinking too much about how did they do the derivation. But yeah, zeta 0.707, I think it's coming from here, because here it cannot become greater, otherwise it's going to become negative. And again, we can easily confirm this when we plot the exact plot. We can calculate the value of the peak value from this and then look at the plot and see if those values match. That means this equation must be correct if the two values match. That's an easy exercise to do. All right, Bode plot, phase Bode plot of the second order system. Approximations that we take, we calculate the phase of the second order system. Of course, the phase, let's go back to the equation. Phase of this thing right here, what you have right here. So what will be the phase of this? Minus tangent inverse of imaginary part 2 zeta u divided by the real part 1 minus u square. So minus tangent inverse of imaginary part 2 zeta u over 1 minus u square. And again, remember u is the normalized frequency, which is omega over omega. Approximation, when u is quite smaller than 1, phase is 0. Again, you can do the same thing. If omega is approximately equal to or less or equal to 0.1 omega n, phase is 0. And when u becomes greater than 1, quite larger than 1, again, you can take the approximation when omega becomes greater or equal to omega n, the phase angle will approach negative 180 degrees. Why negative 180 degrees? Because again, you have a, let's see, less than 1 is going to be, this will be 0 then, and then you have, this will be taken as 0, the whole thing will be taken at 0, so it's going to be 0. When it becomes quite larger than 1, when omega becomes quite larger than omega n, negative tangent inverse of 2 times zeta omega over omega n, 1 minus omega over omega n square. So when it becomes quite larger than omega n, then we will assume, what we're going to assume, that this number is going to become, wait a minute, it's going to be negative 180 degrees. When omega is omega n, that is going to be 90 degrees. So that is, we will have to apply the L'Hopital rule basically on that, because the denominator is becoming 0. Oh, denominator becomes 0 means it's infinity. So yeah, infinity means that it's a very large number. It's going to become negative 90 degrees at that time. Negative 180. Let's see. Quite large. So it's going to be, we'll assume it's infinity over infinity, and then we will do the L'Hopital rule. To do that, it's going to become tangent inverse of I'll have to do that. Let's just go with this right now. I'll have to think about it. Why did I put negative 180 degrees? U is quite smaller than 1, phase is 0. Quite larger than 1, phase is negative 180, and at 1 is going to be negative 90 degrees, which is easy to see. It's negative 90 degrees at u is equal to 1 in the equation. Negative tangent inverse of 1 over 0. Phase response looks like this for different values of zeta. Again, these are the not the approximate, but these are the exact phase responses. Approximate, you go until 0.1 omega n, 0, and more than 10 omega n, negative 180, and then you drop it by negative 90 degrees per decade. Summary of different terms that we did. If you have a value, gain value, of course, it's going to be constant. Phase angle will be 0. If you have a 0 until the cutoff frequency is 0, and then it's going to increase by 20 decibel per decade. If you have a pole, first order pole, until the cutoff frequency is 0, then it's going to drop by negative 20 decibel per decade. Phase is going to drop by negative 45 degrees per decade. If you have a pole at the origin, 1 over j omega, then it's going to drop by negative 20 decibel per decade. And if you have the second order system, then until u, they're showing 1, and then after u is negative 40 decibel per decade. But again, you will have to do some approximation here. You have to go until 0.1 as your 0, and then you will have to find the peak value based on omega, and then you'll have to go like this. Something like that is going to be the second order system. And the phase response of the second order system, again, it's going to be a little bit of curve until 0.1. And then, so no, it's going to go negative 90 degrees per decade. For the exact plot, it's going to be a little bit of curve over here. But for the approximate plot, that's how it's going to be. So usually we have to show that, of course, peak value for the second order system. All right, let's see. Bode plots are created from a transfer function of the control system. The transfer function can also be deducted from the Bode plot. That's one of the problems actually I gave you in the homework. I gave you the Bode plot, and then I asked to write down the transfer function. Let's see, what transfer function do I have here? I did not put it. Let's see. If we have a Bode plot, something like that, omega magnitude of transfer function in decibel. So if our Bode plot isn't the same I gave you in, I don't know if it's the same I gave you. This is 50 decibel. This is 100 radian per second, 20 dB per decade. $1,000, and this is 10,000, and this is negative 20 decibel. If this is given to you, I think it's the same as the homework problem, if I remember correctly. I don't know. If this is given to you, and we have to write the transfer function corresponding to this Bode plot, how are you going to find that transfer function? So of course, identify that. What do you have? You have 50 decibel constant. Then you have a 0, 20 decibel per decade is starting at 100 radian per second. Then since it becomes constant again here, you're going to have a pole here that is going negative 20 decibel per decade. And finally, you have a pole at 10,000, which is going at negative 20 decibel per decade. So this is comprised of 4 different functions: a constant value, 1, 0, and 2 poles. The constant value is 50 decibel per decade. From that, you can calculate the value of the gain. So the first factor is 50 decibel per decade. Are we going to find K? Who's going to tell me? What will be the value of the gain? Yeah, it's written here. 50 is equal to 20 log 10 of K. How are we going to find K? Okay. 50 or 20? Yeah. I'm sorry? Exponent. Well, the base is 10. If it's a natural log, then you take exponent. Yeah. the base is 10. If you do natural log, that's the base e. For that, you're going to take exponent. Yeah. But since the base is 10, so 10 to the power 50 over 0. 316.23. All right. And we know that. So let me write this down then. T of j omega magnitude is equal to 316.2 plus 1 plus 20 log of, actually, let's write this down. I'm thinking of the best way to write it down. So you have 1 plus, again, this is going to be 1 plus j over 100. 1 plus j over 100, j omega over 100. And then you have for these two, 1 over j omega over 1000 and 1 plus j omega over 10,000. Magnitude of this. Right? So the transfer function Ts is going to be 100. So S plus 100, 316.2, S plus 100 over 100. So over 100. S plus 1000 over 1000 and S plus 10,000 over 10,000. So let's calculate the gain value. 100 is 10 times 1000. So 316.2 times 10 times 1000, so 10,000. 316.2, 10,000 is what? Exponent 4. Exponent 4. S plus 100 over S plus 1000. S plus 10,000. 316 exponent 4 is 3.16 exponent 6, right? 3.16 exponent 6 to be in the engineering notation. That will be the final transfer function of this thing. Question? Any question about this? Yes. Poles are the one that are going down, right, in the denominator, and zeros are the one in the numerator, which is the 20 decibel per decade that's going up. That's the zero, and negative 20 is the one that is going down. Those are the poles. Yeah. Mm-hmm. Time it is 12 o'clock. All right, I have a little bit of left, and I think I already put down everything. So let's go over it quickly. 3 or 4 slides that we have. Yes, go ahead. Yeah. A double zero and pole where? So you're saying why we, so there's, you're saying there could be a double zero and double pole at 100 and 10, but that's going to cancel each other out, right? And the numerator and denominator, whether they're the single zero or pole or double zero, they're going to cancel each other out. The same factor in the numerator and denominator. All right, let's look at this. This is from the book, of course, but I put down the plots and stuff to discuss this. Design example in which we will explore the parameters of a controller to control a photovoltaic generator to yield maximum power as the output of the generator varies due to the variable sunlight, temperature, and the load connected to the generator. Of course, we know that different sun exposure is going to produce different sunlight, different power from the photovoltaic, the panels. Temperature affect the panels as well. And I think I discussed it in my power systems class, if you're in my power system class. What I read online is, I believe 77 Fahrenheit is the optimum temperature at which the maximum production occur from the solar panels. And as you go above 77, then the production starts going down. So generally, let's say in Central Florida, generally in March, April, you generally see the maximum production because the temperatures are around like between 70s and 77. But these days, with 100 degrees or 90 degrees, generally, even though we have longer days, but the total generation of power, if you have solar panels, like I have solar panels, they're not, even though the day is longer, but the total power generation is lower than what I was getting in April, basically, when the temperature were around that, sweet point around 75 or something like that. So increase of temperature, and that's why I did some research online and found out that around 77 degrees, I think, is the optimum temperature, and after that, the power starts going down. It does not produce as much of a power as around 76, 77 degrees. So temperature does affect the production of power through solar panels. And of course, the load that is connected to the generator, it can produce some loading effect, and it can reduce the overall efficiency of the generation because you can have more losses at the inverter and all those places. As the current increases, then you start getting more losses. To increase the overall efficiency of the photovoltaic generator, feedback control strategies can be employed to seek to maximize the power output. This is called the maximum power point tracking. Certain values of current and voltage associated with the solar panel corresponding to the maximum power output. Maximum power point tracking uses closed loop feedback control, as you can see in this block diagram. You have the controller, and then you have the process, which is the solar panel, basically. Power circuit, photovoltaic generator, and circuit, the current transducer. The block diagram shown in figure 8.6, the previous page, can be represented with the transfer function of controller and plant, as you can see in figure 8.7. Photovoltaic generator with, so this is an example of photovoltaic generator with 182 cell generating over 1.1 kilowatt of power. The value of K is around 300,000 in this, right here, this K, and the value of P is 360. Controller gain Kc, and the time constant tau1 and tau2, we have to determine what are their values for the optimum power generation. The controller shown is called lead or lag compensator. And I think in the next chapter, chapter number 10, I'm planning to cover at least one of them, either lead or lag, or both if I find time, because I still have to create notes for the second chapter, for the last chapter 10. The controller shown is called lead or lag compensator depending on the value of the two-time constant. The goal of the controller design is to minimize the effect of disturbance and the planned changes by providing a high gain at low frequencies while minimizing the measurement noise by providing a low gain at high frequencies. To accomplish these goals, we have a specifications that the magnitude of the gain for the GC and G, so this is GC and G, it's not written here, but it's pretty obvious that this is GCS and this is GS. GC and G, the gain at as a function of frequency should be greater or equal to 20 decibel for the frequencies less than or equal to 10 radian per second. That's one of our goals. And again, this is to minimize the effect of disturbance. Or sorry, minimize the high gain at low frequencies. So minimize the measurement noise basically at low frequencies. And GC and G has to be less or equal to negative 20 decibel. So attenuation of negative 20 decibel or less for high frequencies to reduce the effect of the disturbance. Phase margin has to be greater or equal to 60. So this is the first time we are looking at the phase margin. So what is phase margin? So phase margin is the measure of the stability of the control system, and it is measured from the phase Bode plot as the difference of the phase at the frequency where gain of the system is 0 decibel. So whatever phase you're going to see when the gain of the system is 0 decibel. So you look at the frequency at which 0 decibel is happening, and then you look at the phase Bode plot at that frequency and observe whatever the phase of the system at that frequency, and negative 180 degrees. So phase margin is generally, phase margin is the frequency, the phase at the frequency when your magnitude is, the magnitude, let's say G, C, G is 0 decibel. The phase at the frequency where your magnitude is 0 decibel minus 180 degrees. That's the phase margin. The frequency where gain of the system becomes 0 decibel is called the crossover frequency. So what we're going to do, we're going to plot the both magnitude and phase Bode plot for the uncompensated system. GCS is equal to 1 to get an idea as how much compensation is required from the controller as far as gain and phase margin is concerned. So we're going to take GCS to be equal to 1, and we are going to plot the phase Bode plot. Let me see where it is. So we are plotting basically for this function when k is 300,000 and p is 360. K is 300,000 and p is 360. And GCS is equal to 1 right now. So that's the Bode plot of, should write it down here so that, so this is the Bode plot, magnitude Bode plot of GCS GS. GCS is 1 and this is 300,000 over S times S plus P. Let's draw it again. Let's see if this is the one we're gonna get, because I forgot if this is, I'm pretty sure this is it. Let's try it though. package load control, and my system is $300,000. And then 0, 260. No, I have to get polynomial. So s square plus 360. So s square 1, 360, 1, 0. S square plus 360, yes. And then we do Bode of system. That's the Bode plot. And I'm assuming this is the same as what I have here. Starting at 40, and I think it's the same, yeah. So this is the Bode plot when your controller gain is 1, and we are plotting basically for GS for those values. And this is the exact Bode plot, of course. Okay. So now we are trying to figure out what is the crossover frequency. That is, at what time the gain is going to become 0 from the magnitude response. So right here, this is your crossover frequency. About 500. It's hard to see over there. Maybe if you do it in MATLAB, it's gonna show you clearly when you click on that. But it's around 500 radian per second, which I put right here. So the crossover frequency at which the gain becomes 0 is 500 radian per second. All right, now you go to the crossover frequency, which is 500 radian per second in the phase. 500 radian per second. So this is 100 or 500 is this, right? So you go here and then read what the phase is going to be. It's about negative 144 degrees, right? Negative 144 degrees. Let me see, what did I put it? Negative 144 degrees minus negative 180 is equal to, let me see, negative 144 degrees minus negative 180. So the phase margin is about 36 degrees. That's the phase margin. Minus negative 180 degrees, not minus 180 degrees, minus negative 180 degrees. So that's how we are reading the phase. That's how we are calculating the phase margin. Going at when the gain becomes 0, looking at that frequency from the magnitude plot, and then going to the phase Bode plot and looking at what value of phase do we have at that frequency, which is 500 radian per second. So at the bottom, you can see it's negative 144, and that's what we get the phase margin. So here, Bode plot will show from the magnitude Bode plot. Where is it? Right here. Okay. Oh, I skipped this slide altogether, I guess. Yeah, I skipped this slide. So no, I didn't skip it. Actually, I was just trying to figure out. So from figure, we saw that phase Bode plot for GS can observe that the gain at 10 radian per second is greater than 20 degrees, thus satisfying the first requirement. So from the magnitude Bode plot at 10 radian per second, which is the first value actually, right? Or is that, let me go to my, This is 10 to the power 1. So at 10 radian per second, your gain value is, of course, greater than 20 decibel, which was the first design parameter that was given to us. Greater than 20 decibel for less or equal to 10 radian per second. This is 10. So it's greater than 20. That's what I wrote down here. That satisfies the first requirement already. However, the gain at 1000 radian per second is negative 11 decibel, because the second requirement was that greater or equal to 1000 radian, it has to be less than negative 20 decibel. So in the figure, when you go to 1000, which is this 10 to the power 3, your gain is negative 11.4 or negative 11 decibel, which is larger than this requirement because it has to be less or equal to negative 20 decibel gain. So it's larger than that second requirement. First requirement is satisfied, second requirement is not satisfied. And the phase margin should be greater or equal to 60 degrees. Our phase margin is coming out to be 36 degrees, which is not greater than 60 degrees. This means that the compensation circuit must increase the gain margin by at least 24 degrees. It has to be a phase lead circuit, basically. So what did we do? First, we did the Bode plot for the uncompensated system. Uncompensated means that you are not providing any gain right now from the controller. It's only the plant transfer function, and you're plotting that plant transfer function without providing any gain. So you observe that uncompensated system, you satisfy the first requirement, but the other two requirements are not satisfied for that. So you have to perform some sort of gain compensation. And since you have to increase the phase margin, we have the phase lead circuit. If you have to reduce the phase margin, then it's going to be phase lag circuit that you have to create. So again, this is from the book. So I did not do it myself. So in the book, one of the possible configuration that is given for the controller to achieve the given requirement is if we take the controller transfer function and gain as given by that 250, tau 1 is 0.4, and tau 2 is 100. So we calculated the transfer function of this. 30,000 s plus 25, s times s plus 01, s plus 3. And Bode plot of the loop gain are shown in figure 8.9. So now GCS GS, we have this updated transfer function. And then we plotted this updated transfer function, Bode plot of this updated transfer function, GCS GS. And this is our magnitude, and this is our phase. So again, we are good with at omega is equal to 10. We are good with the gain. It is greater than 20 decibel. We go to 1000, and the gain is negative 35 decibel. Again, this is good because it's less than negative 20 decibel at 1000 right here. And the crossover frequency is coming out to be about, what is that, 85 radian per second. Instead of 500 radian per second, it is 85 radian per second. And at 85 radian per second, we observed that margin, phase margin, it was coming out to be 61.5 degrees. So whatever the phase is coming out to be, negative something, we can do it because it's hard to see over here. Let's just do it real quick just to see. System 2 is equal to transfer function transfer function of all right, this is better. So 30,000 S 30,000 and 30,000 times 25, That's our numerator, and our denominator is s cube. So let me just create the denominator using poly function. So poly, my first root is 0, my second root is negative 0.01, and my third root is negative 360. So s cube plus 360 s square plus 3.6 s. And then figure 2 and Bode of system 2. Bode of system 2. Oh, this is not the, it's not the same that I'm getting over there. Oh, my frequency is starting early. Okay. For some reason, it started frequency at 10 to the power negative 3. And I'm looking over there at 10 to the power 1. I wonder if I change the frequency over here. But here I'm starting at 10 to the power, what is that frequency? 10 to the power 0. So I'm starting at 1. This is 10 to the power 1. And here in figure 2, it's starting at 10 to the power negative 3. So this is 10 to the power 0. I'm starting here in that, right over here. So let's observe starting from here. Crossover frequency is 70, around 77, 79 or 80 or something like that. So right here, the phase is negative 120 approximately, negative 119.5. And all right, phase margin is around 61.5. So negative 119.5 plus 180, about 60.5, yeah, approximately 61. I'm putting 61, perhaps measurement was different. Around 60.5, which is still greater than the required one. So all the three values are satisfied. All the three conditions are satisfied. At 1000 right here, your attenuation is negative 32, which is less than the attenuation required, which is negative 20 decibel. So using this controller gain, we can satisfy all three conditions, and our system is the phase, the compensation circuit is the phase lead circuit. How we got to that, I think in the next chapter, we're gonna see how we got to this phase lead compensation circuit, because that the design is in the next chapter for that. Or design of phase lead and phase lag is in the next chapter. So again, this is an example of how to use Bode plot in order to design a system for the given specifications. This is from the book, but I added the Bode plots and all those things and all the description over here. And this is your step response for that system using the transfer function, as you can see. And it calculates the peak value, peak overshoot, and the steady state value and all those things. And that concludes this chapter. So I'm going to post another set of homework with phase. You did magnitude Bode plot for the first order. I may have some more magnitude Bode plot, phase Bode plot, first order, second order system. So make sure to do that. I'll try to post it today. I don't know if I have some, but I'll have to make a homework set, I think. But I'll try to make one and then post it. As far as project is concerned, keep working on the project. And let me stop recording and then we can discuss.